Hi students, welcome back to the another finite element analysis session. My name is P.NAVIN JASS, Assistant Professor, Department of Mechanical Engineering, Rohini College of Engineering and Technology. Today we are going to study about the one-dimensional linear bar element problems. Okay, in Unit 2, already we study about the one-dimensional linear bar element introduction. Today, we are going to see one problem about one-dimensional linear bar element. Okay, this is the problem. Now I read the question. Consider a bar as shown in figure. An axial load of 200 kilonewton is applied at a point P. Take A1 is equal to 2400 mm square. E1 is equal to 70 into 10 to the power 9 Newton per meter square. Then A2 is equal to 600 mm square and E2 is equal to 200 into 10 to the power 9 Newton per meter square. Calculate the following. The nodal displacements at point P, stress in each material and reaction force. Okay, this is the diagram. There's a step to bar element fixed at both the ends. At the middle of the bar element, there's a load is acting 200 kilonewton. There are two elements separated. One is the first element and the second element. They given a naming it as a first element and second element. For the length of the first element is 300 mm and length of the second element is 400 mm. Okay, here a bar is given. A bar consists of two elements. Normally we call it as a stepped bar element. This stepped bar element is fixed at both the ends. Here, the first element, length of the first element is 300 mm and length of the second element is 400 mm. The load is acting at the mid of the stepped bar at 200 kilonewton. Now, the area of the first element is 2400 mm square. Area of the first element is 2400 mm square. Here they are given as A1 is equal to 2400 mm square. Likewise, for the second element, area is given A2 600 mm square. 600 mm square. Likewise, for the first element and the second element, here E1 and E2 is given. E1 and E2 is nothing but Young's modulus for the first element and Young's modulus for the second element. For the first element, Young's modulus 70 into 10 to the power 9 Newton per meter square is given. For the second element, 200 into 10 to the power 9 Newton per meter square. Here, we should calculate the nodal displacements at point P. The nodal displacements at point P. Then stresses in each material. Stresses in each material. We should find out the stress for the first element and also for the second element and the reaction forces. And also we should find out reaction forces. Well, nodal displacement at point P means there is two elements. Both the ends of the stepped bar is fixed. So the question itself they given both the ends are fixed. So there is no displacements at both the ends. So only they given. You should find out the displacement at the mid of the stepped bar, which means the point P. Okay, now we are going into the problem. Okay, here we simplify the diagram for our convenience. Normally, for each element there are two nodes. Here, for the first element, we are giving two nodes, node number 1 and node number 2. node number 1 and node number 2. Then length of the element is 300 mm. Length of the element is 300 mm. And for the second element, we are giving two nodes, node number 2 and node number 3. Node number 2 and node number 3. Here the length of the element is 400 mm. Length of the second element is 400 mm. And the load 200 kilonewton is acting at the mid of the stepped bar, which we call it as a point P. That point P is called as now U2, which U2 or node 2. So we should find the value of U2. Find the value of U2. Here already we saw in the question, area of the first element 2400 mm squared, area of the second element 600 mm squared, length of the first element 300 mm squared, and length of the second element 400 mm squared. And Young's modulus of the first element 70 into 10 to the power Newton per meter squared. We are going to convert this Newton per meter squared into Newton per mm squared. So 70 into 10 to the power 3 Newton per mm squared for Young's modulus for the first element, and for the second element 200 into 10 to the power 3 Newton per mm squared for the second element. Now the point load. Point load is in kilonewton. We are going to convert it into Newton. So 200 into 10 to the power 3 Newton. 200 into 10 to the power 3 Newton. Here already you saw in the question, to find out the nodal displacements at point P and stresses in each material sigma 1 and sigma 2 and reaction forces R1 and R2. R1 and R2. So now we are going into the problem. The formula for the finite element equation for one-dimensional two-noded bar element. One-dimensional two-noded bar element is F1, F2. Vector matrix of F1, F2 is equal to AE by L matrix of 1, -1, -1, 1 into vector matrix of U1, U2. This is the general finite element equation for the one-dimensional two-noded bar element. Now, by using this general finite element equation, we are going to find out two equations for two elements. Two equations for two elements, for the element number 1 and for element number 2. For element number 1, first we are taking the first element. Here we are having two nodes, node number 1 and node number 2. Here point load is acting at node number 2. The length of the element is 300 mm and U1 is here, U2 is here. Okay, now we are substituting the values in the given finite element equation. Here F1, F2, we don't know the value of F1 and F2. Likewise, we know the value of area. Area for the first element is 2400 mm square. 2400 mm square. Then for the first element, Young's modulus 70 into 10 to the power 3 Newton per mm square. 70 into 10 to the power 3 Newton per mm square. Now length of the first element is 300 mm. Length of the first element is 300 mm. So now we are substituting these values in the above finite element equation. So here A1 into E1 divided by L1 matrix of 1, -1, -1, 1 into vector matrix of U1, U2 is equal to vector matrix of F1, F2. So substituting the A1 value 2400, Young's modulus value 70 into 10 to the power 3 and length of the first element 300 mm. So after calculating this 2400 into 70 into 10 power 3 divided by 300 is, the value is 5.6 into 10 to the power 5. 5.6 into 10 to the power 5. So we are substituting the 5.6 inside the matrix. Now 1 into 10 to the power 5 matrix of 5.6 minus 5.6, minus 5.6, 5.6 into U1, U2, into U1, U2, which is equal to vector matrix of F1, F2. First element equation we found out in this problem. Now for the second element, we are having nodes 2 and 3. We are having the nodes 2 and 3. Here, the point load is acting at point node 2. So 210 to the power 3 Newton. And the length of the second element is 400 mm. We have the value of area is 600 mm squared. Young's modulus 200 into 10 to the power 3 Newton per mm squared. And length of the element is 400 mm. So now we are substituting these values in this equation, and after multiply this equation 600 into 200 into 10 to the power 3 divided by 400, we are having the value of 3 into 10 to the power 5. We got the value of 3 into 10 to the power 5. So we are multiply the 3 inside the matrix and 1 into 10 to the power 5 outside the matrix. So 1 into 10 to the power 5, 3 minus 3 minus 3, 3, U2, U3, which is equal to matrix of F2, F3. This is the second finite element equation. Okay, we got the two elements equation, but the element is a single stepped bar. It is a single stepped bar. Okay, there are two elements. That two elements are merged and it is a single stepped bar fixed at both the ends. So now we are going to assemble the above two equations that we found out for the first element and second element. Now we are going to assemble the two equations. So how we are going to assemble? For the first equation, we got the value of 1 to 10 to the power 5, 5.6 minus 5.6 minus 5.6, 5.6. So we are giving the naming or numbering for the each element number. So for 5.6, we are giving the naming as A11, minus 5.6 as A12, minus 5.6 as A21, 5.6 as A22. So 1 into 10 to the power 5 and this equation. Now for the second equation, we are giving the naming as, why we are giving this naming 1, 1 and 1, 2 means here the node is from, for the first element is 1 to 2, 1 to 2. So we are giving for the first element, first row A1, we are giving for the first node and A1 second node. Likewise, for the second row A2 first node, A2 second node. Okay. Likewise, for the second element, we are giving naming as for 3 A22 minus 3 A23 and minus 3 A32 3 A33. Why we are giving here A22 A23? Because here there is no first row. It is start from the second one. So we are starting it from the second one. So A22 A2 second node, A2 third node. Likewise, A3 second node, A3 third node. By this, we are giving the naming for this matrices. Now we are going to assemble. Here we are, for assembling, we are giving the again naming A11, A12, A13, A21, A22, A23, A31, A32, A33. Now we are substituting the values in this matrices. How we are going to substitute for? Now we are substituting the A11, A12, A21, A22 values in this equation as 5.6 minus 5.6 minus 5.6, 5 and 5.6. But here A22 value is A22 value is again repeating. So with this 5.6, we are going to add this 3 A22 value. There are two A22 values. One is 5.6 and 3. So now we are adding this value. So 5.6 plus 3 minus 3 minus 3 3. So here A13 and A31 is not in the above two equations. So we are giving us 0. So we are giving us 0. Now the equation changed. 1 into 10 to the power 5. The assembled finite element equation is 1 into 10 to the power 5 matrix of 5.6 minus 5.6 0 minus 5.6 8.6 minus 3 0 minus 3 3 and vector matrix of u1 u2 u3 which is equal to vector matrix of f1 f2 f3. So this is the assembled stiffness matrix equation. This matrix is the 5.6 minus 5.1 into 10 to the power 5, 5.6 minus 5.6, 0 minus 5.6, 8.6 minus 3, 0 minus 3, 3. This is the assembled stiffness matrix equation or stiffness matrix. Now we are going to apply some of the boundary conditions that is given in the question. What are the boundary conditions? First one, displacements at node 1 and 3, which we call it as u1 and u3 is 0. Why it is 0? Because in the diagram itself they are given. Here the first, both the ends are fixed. For the first node and the third node it is fixed. So there is no displacements because it is fixed. There is no displacements in the both the sides. So for that purpose, they are given in the boundary conditions. Displacements at node 1 and node 3 is 0. So u1 and u3 is 0. Is equal to 0. u1 is equal to 0 and u3 is equal to 0. Now at node 2, 200 into 10 to the power 3 Newton load is active. At node 2, 200 into 10 to the power 3 Newton load is acting. So F2 is equal to 200 into 10 to the power 3. From the diagram itself, they are given. At node 2, 200 into 10 to the power 3 Newton load is acting. So they are giving. So now we are giving F2 is equal to 200 into 10 to the power 3 Newton. Here they are not considering the self weight. Here in the question, they didn't mention about the self weight. So for that purpose, we are neglecting the self weight. For that purpose, we are neglecting the self weight. So F1 and F3 is equal to 0. Already we have the value of F2. So here F1 and F3 is equal to 0. Now we are going to substitute all the boundary condition values in the above assembled finite element equation. So 1 into 10 to the power 5, 5.6 minus 5.6, 0 minus 5.6, 8.6, minus 3, 0, minus 3, 3. This is the stiffness matrix. Now, in displacements values, vector matrix of U1, here U1 is 0. So now we are putting U1 is equal to 0 and U3 is 0. So now we are putting U3 is equal to 0. We need to find out the value of U2. Which is equal to, here we are neglecting the self weight, so F1 and F3 is equal to 0. F1 and F3 is equal to 0. So here F2 is equal to 200 into 10 to the power 3 Newton. So 2 into 10 to the power 5. Instead of here 200 into 10 to the power 3, we are substituting 2 into 10 to the power 5 Newton. 2 into 10 to the power 5 Newton. Okay, now in the above general finite element equation, we are considering u1 and u3 is 0. In this equation, u1 and u3 is 0. For that purpose, we are neglecting the first row, first column, and third row, third column. So we are neglecting the first row, first column, and third row, third column. So the balance number is 8.6. U2 is equal to 2 into 10 to the power 5. 1 into 10 to the power 5 into 8.6 into vector matrix of U2 is equal to 2 into 10 to the power 5 is the balance in the general finite element equation. So we are taking 8.6 into 10 to the power 5, U2 is equal to 2 into 10 to the power 5. So 8.6 into U2 is equal to 2 because here 10 to the power 5 and 10 to the power 5 is cancelled. So U2 is equal to 2 divided by 8.6. So the final value of U2 is equal to 0.2325 mm. While we calculating with the help of the calculator, we got the value of U2 is equal to 0.2325 mm. Now, we are going to find out the stresses in each element. To find out the stress in the element, we are going to use the formula sigma is equal to Young's modulus into du by dx. Sigma is equal to Young's modulus, which is stress equal to Young's modulus into du by dx. So here, sigma 1, for the first element, we are going to find out the stress value. Sigma 1 is equal to Young's modulus 1. We know the Young's modulus value, 70 into 10 to the power 3. Into U2 minus U1. We find out the value of U2 and already we know the value of U1 is equal to 0 divided by length of the first element. So 70 into 10 to the power 3 into 0.2325 is minus 0 divided by 300. After calculating with the help of the calculator, we got the value of sigma 1 is equal to 54.25 Newton per mm square. Likewise, we are going to find out the stress for the second element. Sigma 2 is equal to E2 into U3 minus U2 divided by L2. So for 210 to the power 3 into 0 minus 0.2325 divided by 400. So sigma 2 is equal to minus 116.25 Newton per mm square. We got the stresses value. Sigma 1 is equal to 54.25 Newton per mm square. Likewise, sigma 2 is equal to minus 116.25 Newton per mm square. Now, we are going to find out the reaction forces value. To find out the reaction forces in the given stepped bar element fixed at both ends, reaction force R vector is equal to, R vector matrix is equal to stiffness matrix K into vector matrix of U star minus vector matrix of F. So here there are three nodes. So we are going to find out reaction force for the three nodes R1, R2 and R3 is equal to stiffness matrix value 1 into 10 to the power 5, 5.6 in minus 5.60, 5.6, 8.6, minus 3, 0, minus 3, 3 into vector matrix of U1, U2, U3 minus vector matrix of F1, F2, F3. So now with all the values, we are going to substitute in this equation. R1, R2, R3 is equal to 1 into 10 to the power 5 matrix of 5.6 minus 5.60 minus 5.6, 8.6 minus 3, 0 minus 3, 3 into vector matrix of 0.2325, 0 minus 0.2 into 10 to the power 5, 0. Okay, here now we are going to find out the value for this R1, R2, R3. We are going to multiply the matrix equations into row into column, row into column. So here 5.6 into 0, 0 minus 5.6 into 0.2325 plus 0 into 0. Likewise, for all the rows into columns, minus 5.6 into 0, 0, 8.6 into 0.2325 plus 0 into minus 3 into 0. For the third row, 0 into 0, 0, minus 3 into 0.2325 plus 3 into 0, 0, minus 0, 2 into 10 to the power 5, 0. So what's the finally R1, R2, R3 value? 1 into 10 to the power 5 minus 1.302, 2 minus 0.6975 minus vector matrix of 0, 2 into 10 to the power 5, 0. Now we are going to subtract these values. So finally we got the R1, R2, R3 value is equal to minus 1.302 into 10 to the power 5, 0, minus 0.6975 into 10 to the power 5. So the final values for R1 value is minus 1.302 into 10 to the power 5 Newton, R2 is equal to 0 Newton and R3 is equal to minus 0.6975 into 10 to the power 5 Newton. So the final result is for nodal displacement at point P, U2 is equal to 0.2325 mm stresses in each materials, sigma 1 is equal to 54.25 Newton per mm square and sigma 2 is equal to minus 116.25 Newton per mm square, and the reaction force is equal to R1, R2, R3. So R1 is equal to minus 1.302 into 10 to the power 5 Newton per mm square. R2 is equal to 0. R3 is equal to minus 0.6975 into 10 to the power 5 Newton per mm square. So by this session is over. We are going to see the next problems in the upcoming session. Thank you.